In this video, we'll continue our discussion of hydrogen with the hydrogen molecule. We'll first start by reviewing the hydrogen molecule ion solution. Then we'll define hydrogen molecule coordinates. And finally, normalize the wave function and compute the final bond length and energy. So, if you recall, the Hamiltonian for the hydrogen molecule ion has two protons separated by a distance r and one electron. The vectors between the electron and the individual protons were labeled as r1 and r2. The Hamiltonian was given by the Laplacian times minus h bar squared over 2m for the electron minus e squared over 4 pi epsilon naught times 1 over r1 plus 1 over r2, which is the potential energy of the electron with respect to each of the two protons, proton 1 and proton 2. And then we had a term for proton-proton repulsion, which prevents the protons from getting too close to each other, which is e squared over 4 pi epsilon naught times capital R. The trial solution was a linear combination of atomic orbitals centered about each of the protons. So we had A times the quantity psi 0 of R1 plus psi 0 of R2. And from this, we derived three integral quantities, one from the normalization, which is called the overlap integral, which is called I, defined as I, which is e to the minus r over a, times 1 plus r over a, plus 1/3 r over a squared. And then we had, for the potential energies, we had two integrals. One was the direct integral, which worked out to be a over capital R minus 1, is the quantity 1 minus a over capital R times e to the minus 2r over a. And the exchange integral, which we defined as x, being e to the minus capital R over a times the quantity 1 plus capital R over a. The total expectation value of the Hamiltonian was then given in terms of these three integrals as 1 plus 2 times the direct integral plus the exchange integral divided by 1 plus the overlap integral minus 2a over capital R, which is the term from the proton-proton repulsion, all times the energy of a hydrogen atom. And when all these values were put in, you can plot these as a function of r over a being x. So if you define r over a as x, this gives you 1 over x, this gives you 1 over x, and now here we have e to the minus 2x, and so on. And when that's plotted, you get the following system. The function goes at infinity to E1, which is the energy of a single hydrogen atom, which makes sense because as you pull the protons far enough away, you get one isolated hydrogen atom with a proton on the other at the other infinity, infinitely far away. When you bring the protons very close together, the repulsion gets very high, and you can see that the energy goes high. In between, the energy drops below the energy of a single hydrogen atom and has a minimum at an equilibrium position. And we calculated what the equilibrium position was in terms of the Bohr radius A. And you can calculate what the energy minimum value of the minimum is as well. And they were estimates. They weren't exactly right because the trial function is a variational trial function, and it only gives you an upper bound on the energy. And of course, there may be better ways of doing this than just using the hydrogen wave functions alone. We'll now take on the hydrogen molecule by adding an electron to the Hamiltonian. So we have now 2 electrons and 2 protons. Well, now we want to change our coordinate system a little bit. We will now define the protons as primed and unprimed protons, and the electrons as 1 and 2. So we have R1 is the distance of the first electron, electron 1, to the unprimed proton. R1 prime is the distance of that first electron to the primed proton. Similarly for R2 and R2 prime. And then we have R12, which is the distance between, or the vector between the two protons. The Hamiltonian now includes a few more terms. We now have the kinetic energy with the Laplacian for electron 1 plus the Laplacian for electron 2. The potential energy has the same common form on the front, which is E squared over 4 pi epsilon naught. And now we have 6 terms. We have the direct Coulomb interactions between electron 1 and each of the protons, the primed and the unprimed protons. And then we have the same direct Coulomb attraction with electron 2 with the unprimed and primed protons. We have the proton-proton repulsion, which is 1 over capital R. And then we have the electron-electron repulsion, which is 1 over R12. So we now have a few more terms to calculate. We also have to define a different variation wave function because now we have a 2-electron system. And with 2 electron systems, we have to observe proper anti-symmetrization of the wave function. So we can define symmetric and anti-symmetric combinations of 2 hydrogen atom wave functions. We'll call them psi plus minus of R1, R2. One of these, they have a normalization constant A plus minus, and then you have psi 0 of R1, psi 0 of R2 prime, plus or minus psi 0 of R1 prime, psi 0 of R2. So this means electron 1 around the unprimed proton, electron 2 around the primed proton, and vice versa. Now the reason you have this linear combination is because you have identical particles, and you must have your wave function be an eigenfunction under the exchange of the 2 particles. And when you exchange the 2 particles with just one of these, you get the other one. So the symmetric function gives you a positive value for the eigenvalue, and the negative one gives you negative value because it flips the sign of the wave function. Well, now we have to also introduce spin. So because psi plus is symmetric under exchange, it requires a singlet spin function. That is, with the 2 electrons oppositely, in the opposite spin directions. And psi minus is anti-symmetric in space and requires a symmetric, or the triplet, spatial function, spin function for the 2 electrons. So that is the other combination, the symmetric functions, and having the symmetric function of the 2 opposite values of spin, and the 2 states with both spin up and both spin down. A priori, it's not clear which will have the lowest energy, so we have to compute them both. So we have to carry through both psi plus and minus throughout the calculation. Now we're going to do a sort of abbreviated calculation here because most of the actual calculations have already been done for the hydrogen molecule ion, and then they can be done in problem 814, as I'll note later on. So here's our trial wave function. Psi plus minus of R1, R2 is equal to A plus minus psi 0 of R1 plus psi 0 times psi 0 of R2 prime plus or minus psi 0 of R1 prime, psi 0 of R2. We want to normalize both of the trial functions. Well, that's easy enough. When we take the psi plus or minus squared and integrate it over the 2 coordinate systems of the 2 electrons, we get a bunch of terms. First, we have the term where this is multiplied times itself. So that gives us integral psi 0 of R1 squared d cubed R1 and integral psi 0 R2 prime squared d cubed R2. We get the term where this is multiplied by itself. Similarly, you have psi 0 of R1 prime squared d cubed R1 and psi 0 of R2 squared d cubed integrated over d cubed R2. And then you have the cross terms. And the cross terms are identical. And they give you, when you rearrange it properly, put the R1s and R2s together, you get 2 plus or minus 2, because the sign gives you either plus or minus, integral psi 0 R1, psi 0 R1 prime, d cubed R1, times the integral psi 0 R2 prime, psi 0 of R2, d cubed R2. Now, these are normalized wave functions, so this is equal to 1, this is equal to 1, this is equal to 1, and this is equal to 1, because it's just a hydrogen state around 1 proton. This integral is simply the same overlap integral that we did for the hydrogen molecule ion, because it considers only 1 electron. This is also the same overlap integral, and we call that I. So, because these wave functions are normalized, hydrogen atom functions are normalized, and we already computed I, we get immediately that A plus minus, when we take the square root, set it equal to 1 and take the square root, is 1 over the square root of 2 times the quantity 1 plus or minus I squared, where I, if you recall, is equal to e to the minus capital R over A times the quantity 1 plus R over A plus 1/3 R over A squared. We can use the same method as for the hydrogen molecule ion to get the total kinetic energy, which is going to be the expectation value of minus h bar squared over 2m del squared for particle 1, electron 1, is equal to E1, the energy of the hydrogen atom, times E squared over 4 pi epsilon naught, times 1 plus or minus I times the exchange integral divided by 1 plus or minus I squared. We don't need to do that calculation again, but we note that this is going to be the same thing for the second electron. So this is also equal to the kinetic energy of the second electron. Then we have the electron potentials compared to one or the other proton, right? The 1 over R1, 1 over R1 prime, and so on. Those all give you the same integrals. So all we need to do is one of those, and that's given by then 4 times, because there were 4 of them, minus E squared over 4 pi epsilon naught expectation value of 1 over R1. This could be 1 over R1 prime, 1 over R2, or 1 over R2 prime. Doesn't matter. We get the same value. And this has gives you minus 4 times 1/2 times E squared over 4 pi epsilon naught A times the quantity 1 plus the direct integral plus or minus 2 times I times the exchange integral divided by 1 plus or minus the overlap integral squared. The final term that we have to calculate is the electron-electron energy, which we'll call VEE. And this turns out to be E squared over 4 pi epsilon naught A times a direct integral sub 2 plus or minus an exchange integral sub 2 divided by 1 plus or minus I squared, where d sub 2 is equal to psi 0 of R1 squared times A divided by R1 2, psi 0 of R2 prime squared integrated over R1 and R2. So this says that what is the expectation value of this repulsive interaction when electron 1 is around, is in a state that's sort of like a hydrogen-like state, and electron 2 is in a hydrogen-like state around the other proton. So there's around separate protons. And that's a direct integral. We also have x sub 2, which, as you might imagine, has psi 0 of R1, psi 0 of R1 prime. So now you have the electron 1 around, in a hydrogen-like state around each of the 2 protons, times A over R1, 2, and then again psi 0 of R2, psi 0 of R2 prime, the second electron also around each of the 2 protons, integrated over R1 and R2. We can now calculate the total energy of the hydrogen molecule for these 2 trial functions. And that gives us the following value. H plus or minus expectation value is equal to 2 times E1, the energy of a hydrogen atom. So the baseline is 2 separate hydrogen atoms, times the quantity 1, minus A over capital R, which is the proton-proton repulsion, plus 2 times the direct integral minus 2 times the direct sub 2 integral plus or minus 2I times the exchange integral minus the exchange integral sub 2, all over 1 plus or minus I squared. The d sub 2 and x sub 2 integrals, as I said before, are done in problem 814. All the other integrals have already been done for the hydrogen molecule ion. And you can plot the final results after putting it all together versus the same value of x, which was r over a. Where this is the proton-proton distance, and this is the Bohr radius. And now we see that it turns out the singlet state is in green, and it looks very much like the hydrogen molecule ion. Of course, the values are different. The distance is shorter, as you might expect, because you have 2 electrons holding the protons together, so a stronger attraction, and that pulls the protons together. And the triplet state, which is red, is about 10 eV higher. The singlet state goes below the asymptotic value, which is that of 2 separate hydrogen atoms, but the triplet state never goes below that value. So this is very, very much like a bonding orbital, where you could put 2 electrons in a bonding orbital, and an anti-bonding orbital. You could put 2 electrons in an anti-bonding orbital, and if you fill this one, you will tend to split. If you go into the triplet state, you will tend to split the 2 hydrogen atoms apart to infinity. They just repel each other and go away. Whereas if they're in the singlet state, they'll be bound. So what are the actual values here? Now note that this is E over E1, so minus 2 is the energy of 2 separate hydrogen atoms. And the proton-proton repulsion, of course, gives you a large value at small distances. The bond length is computed as 1.64 times the Bohr radius. The actual distance is 1.40 times the Bohr radius. So we overestimate the bond length. The binding energy, that is the energy below this value of minus 2, is 3.15 electron volts, and the real value is 4.5 electron volts. So it's, again, the variational method gives you an upper bound, and it is an upper bound, but it's not very close with this particular function. Any spin-spin interaction between the spins of the electrons and the spins of the protons turns out to be 10 to the 5 orders of magnitude smaller, and it's negligible. And this is this particular trial function and approximation to the hydrogen molecule is called the Heidler-London approximation. So we've done hydrogen molecule ion, we've done the hydrogen molecule, and we see how this leads to a bonding and anti-bonding states.